Okay, we're very happy to have Professor Jasmine Walton to continue with her fourth lecture on the topic of Frobenius algebras.
Welcome back. So this is the fourth lecture on Frobenius algebra. First lecture, we talked about Frobenius algebras over the field. Then we set up studying the nodal categories in lecture 2. We introduced Frobenius algebras in the nodal categories. And now all that's going to pay off because we're going to talk about connections to topological quantum theories. I'm going to define this and everything, but hopefully everything will pay off. So these topological quantum field theories, these were formulated by Tia, in Siegel, in Walton, in the late 80s. And I'm going to give you a very crude description of how these work. This is very crude. All right. So suppose that we have a space of a physical system pictured on a manifold. So it's a manifold M, and this is like a space of a physical system. So picture like, I don't know, the earth with the floor or something like that. And we wanted to understand like maybe some states. Some states on this space. In particular, if you want to understand like quantum field states, we can represent this by, let's say, a vector space V. See the quantum field states. But it's really important to understand how these states evolve with time. Okay, so I'm just going to draw the evolving with time with these states moving, picture these states moving here. And the way that we can capture this movement or this evolution of time, we can capture it algebraically by just taking a linear operator form V. So yeah, this is like the Earth, and maybe you're studying like temperature at a variety of points, and you want to understand how temperature changes with time. So we're turning topological physical information into something algebraic. All right. Now we can take another system. Wow, it's still going.
So let us know what happened with
Okay, so let's take another system. Let's say if this is Earth, we can take like Mars or something like this. We can take another system of vectors on here. Maybe they look very different. I mean, I imagine the temperature on Mars is very different. We can capture this by taking another vector space V and then study its evolution of time by looking at a linear operator on V as well. Or V prime as well. Now, maybe we want to understand both systems together. So in order to understand both systems together, what we will do is take a disjoint union of these two manifolds, M and M prime, and algebraically, what this will correspond to is the tensor product of these two vector spaces. And maybe we don't care about the order of these two systems. Maybe we want to be able to swap the two. We don't care what position they're in. And what this is going to correspond to over here is being able to flip across the tensor product, going from V tensor V prime to V prime tensor V. Okay, so basically this transportation, this is what a TQFT is. But of course, I'm going to describe that in more detail. So essentially what a TQFT captures is that you can represent, I would say, the symmetrical nodal category. This is all can be captured in the symmetrical nodal category, objects and maps and product and swapping. You can represent the symmetrical nodal category of topological states by the symmetrical nodal category of vector spaces. That's the philosophy. Okay. But before we get to the concrete stuff, are there any questions? Right. So let's actually make this a bit concrete instead of like working on earthing Mars and taking temperature or wind speed or whatever. Let's make this very mathematical. Let's recall that a symmetric monoidal category. This is a four tuple. You have a category C, an operation on C, a one, and a way of swapping across the tensor product. So again, this is your five filter. This is some object in C. And essentially, this is a way of taking two objects, X and Y, and being able to swap across the monoidal product. But because we're requiring symmetric, we have that you apply the C twice, you get the identity. Okay. So one example of a symmetric monoidal category would be, this actually here. Your basic example of symmetric monoidal categories would be just your category of vector spaces. This is the most basic example. It's algebraic example. So we take the category of vector spaces with your monoidal product being tensor ring over C, your monoidal unit being C. And this C here, this symmetry is just split. Basically, we're framing up what happens on the right-hand side. Now, I need to tell you what the symmetric monoidal category is that's going to frame up what happens on the left-hand side. All right, so in the symmetric monoidal category here, the topological one, this is called a Bordism category. And I'm going to denote this by board in. Sometimes it's denoted by board in n-1. Okay, so I need to tell you what it is as a category. Objects, these are going to be closed, oriented, n-1 manifolds. So for example, if I do n over 2 here, these are going to be closed, oriented, one manifolds, like circles. So basically over here, we would have disjoint union of circles. With some orientation, of course, something like we have some circles going this way, we have some circles going that way. Those are your objects. Your maps. These are going to be nice two or nice in manifolds between your objects. So these are n-dimensional manifolds going from, let's say, a manifold in M to a manifold M that basically, I would say, just respect boundary up to diffeomorphism. So, for example, over here, when I'm going to draw morphisms in the two-dimensional case, I'm not going to like draw these arrows here. So here's one example of a morphism. I got a circle, and I want a nice two manifold between them. Let's draw this thing. Yeah, perfectly fine morphism going from circle to circle. Your identity map, we're still describing the category. This is just the product manifold. So over here, it would look like circle, circle, and I just take the cylinder here. That's your identity. Composition is achieved by just moving. So if I wanted to like move these two morphisms, what I would do is say I first wanted to do the cylinder and glue on this surface, just do like so. So that's the category. That's the category. Now, how's this thing manure? The manure product is going to be given by just taking the disjoint union, putting the circles side by side, putting the manifolds side by side. And the one, this is going to be the empty manifold. Okay, so you take manifold, you take the disjoint union with the empty manifold and the original manifold. And then this C is just going to be swapped. So for example, if I want to illustrate what a swap looks like in a two-dimensional case, just looks like this. Swap. Swap. Okay. Any questions on this?
Yeah, I cannot read something. So what are the maps and dimensional blocks?
In-dimensional manifolds.
Manifolds.
Yeah, manifolds.
Just manifolds.
Yeah, just manifolds. So objects are one-dimensional manifolds over here, and the morphisms are two-dimensional manifolds. Okay. Okay, so that is going to model what's going on over here. Over here. So what is a TQFT exactly? The TQFT our main definition here. If you're given a symmetric monoidal category, say C, with the tensor product of the 1 and the C, a C value in dimensional TQFT, sometimes it's denoted by N TQFT. Okay. This is going to be a symmetric monoidal functor. Symmetric monoidal functor that is of this form. Basically, when it's denoted, it's often denoted with a Z. I go from the Fordism category with an N to B. That's all a TQFT is. It's just basically this is mathematically this is captured with slogan. And
It's not required to stall.
pardon?
It's not required to stall.
Symmetric, no. Yes. Yes, it is. Yeah, I should say that, yeah. Yeah, you do want strong. Yeah. And I should say that traditionally, this C is that. Traditionally, this C is that. Okay. So why do you think would you want to look at these functors? I mean, basically, what happens is that TQFTs actually give you topological invariance. From TQFTs, okay, these produce topological invariance with data from C. I'm going to do a baby example and then I'll do a more complicated example later on. So, for example, if I have the TQFT, the 2 TQFT, let's say Z going from board 2 to, let's say, vector spaces. Well, I have to have that the 1 goes to the 1. So the 1 here is equal to the empty manifold And it has to go to the one here, which is equal to C. And I also have to have that amorphism going from the empty manifold to the empty manifold goes to a map, a linear map going from C to C. So for example, if I have a morphism that starts with something empty and ends with something empty, like something like this, that manifold is going to go to a number field. Right? I'm actually going to compute some of these later on. All right, so it's a way of like measuring or assigning numbers to manifolds. Any questions on those? Now, one cool fact, TQFTs, these are nice functors. These functors, they certainly form a category. They form a category where the objects are, let's say, the NTQFTs. Right? See? And their maps are now going to be a map between functors that preserves the monoidal structure. These are going to be monoidal. These are going to be monoidal natural transformations going from Z to, let's say, another TQFT Z prime. But here's an observation. Observe that our source category, or this stuff over here, it's actually a rigid category. It's actually a rigid category. This is actually rigid. So namely, if I wanted the evaluation morphism on a manifold or on an object N, choose a map that looks like so. And your co-evaluation morphism is a map that looks like so. Well, let's actually draw some pictures of what this looks like for NS2. So these have to satisfy Jimmy applicants. Okay, so for instance, NS2, I have that my evaluation looks something like this. Start with two manifolds, oriented in the right way, and end up at the empty manifold. So I have this noodle. I have this noodle here, that's my evaluation. And then my co-evaluation is like a code noodle. Different macaroni, okay? And these actually satisfy rigidity axioms. Namely, if I write this out, so 1, 2, 3, 1, 2, 2, 1, 2, 2. Okay, so if I do my code and then my noodle in this way, that is equal to just the identity, just by stretching this out. And if I do my whole code noodle down here, and my noodle here, that's also equal to the identity. So this category is rigid. Rigid.
The goal for object is that it's
With different orientation. Those are the orientation. Okay, so why are we even saying this? Why are we even saying this? Also recall that any monoidal natural transformation, going from a rigid or going between functors from a rigid monoidal category to any arbitrary monoidal category, okay, this is actually a monoidal natural isomorphism. Remember, rigidity actually bodies that. So what this basically says is that the source category is rigid, the target category is anything, and we have a category where the maps are precisely these natural transformations. By this fact, we get that the maps are actually natural isomorphisms. So we end up getting that TQFTs actually form a group point. Form a group point. Any questions? Yeah.
Is there any reason for this identity where we draw circles in this fashion? Can they be just floating this?
Yeah, look, I just got it lined up nicely. Yeah. Yeah. Okay. So any other questions? Oh, I'm doing good on time today, okay? Questions? All right, well, now what I want to do is actually examine two TQFTs in detail. So what I need to do is basically analyze what forward two looks like in detail. And what I'm going to do is I'm going to give you generators and relations of this category. The Noidal generator solutions of this category. Here it is. I cheated. What? Okay, work two in detail. So objects are disjoint unions of circles. So basically you have the circle oriented this way, the circle oriented this way. These generate your objects. Right? Your maps, basically what you want to be able to do is take a surface and break it up into components in a nice way so that you can recover any surface by gluing these components. So the components that are really useful are having the cylinder here and having what I call pants, and then this cup here and what I call copants, and this cap here, and then the swap. These generate our maps. Now, you're not going to really have relations amongst these objects. They are what they are. But you have relations amongst these maps. So for instance, if I take 3 inputs, I can end up with one output by doing pants here and then pants here. That's actually going to be the same thing as doing pants here and pants here. And how we see this topologically is what we can basically do is we can just take out like, pretend that this is putty. I mean, that's topology. So pretend this is putty. I'm going to take my finger, I'm going to squish this down, squish, 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 squish. And I'm going to grab this bit and pull it up, and I end up this side. Here, I have a cap here. If I just take this cap and squash it down, squash, 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 I get the cylinder. Squash, 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 I get the cylinder. These two, if I take the mirror images, I get these two relations. Yes. Okay.
You lost the circle in the second.
That
There's 3 circles, now you go to 3 circles.
No, there are two because the cup is not very visible. The second picture, Chelsea, the second picture on the left side.
Yeah.
On the left side, it's not very visible, but there is a cup on the very top. There is a cup that closes that.
Here? The
Yeah,
cup, oh, that
cup,
we can't see.
yeah.
No,
That's a plug.
It's enclosed.
Yeah,
Oh, yeah, there's a cup, so there's 1-to-1.
Yeah.
1-to-1, but thanks for that. Yeah.
so it's the two,
So I capped it off.
yeah.
Okay, and then you have a few morphisms that go, so these are morphisms that go from 3-to-1, 1-to-1, 1-to-3, 1-to-1. These morphisms go from 2-to-2. And basically, if I take my 2 and I merge, and then co-merge, I can end up with either one of these pictures. So again, let's take our fingers, And what I can do is basically go like this. And in this picture, or I can go like this. And with this picture, these should look familiar, by the way. Just so them feel, recognize something. And then we also have this relation. So this is a really nice category. One thing to note, like you don't have like, if I were to like, do a cup and a cap, I mean, this is not equal to, the idea, the Indian. So we don't have that, just do that. Okay. So, remember that TQFT, it takes all of this topological information and it sends it to something categorical, or in the case of that, something linear algebraic. Let's actually send it to like a rigid number category. Okay, so this is going to go to some object A, and this is going to go to the dual of A. This goes to the identity map on A, and I'm just going to label this as M, U, delta, and epsilon. This is B. Mainly M goes from 2 copies of A to A, and this goes from 1 to A. Right? Now, this is already part of my category. These are like extra structure that it takes into account. Okay, so if I think of this image multiplication, what is this saying? This is saying that it is associative, so we have associativity. And then we have unitality. And then we have the co-stop. And then we have the co-stop. And then what is this? The Frobenius law. Yeah. This is the Frobenius law. And this is the commutativity. Commutativity. So what we end up getting is that the circle ends up going to a commutative Frobenius algebra, not annual algebra in C, but a commutative Frobenius algebra in C. Okay, so here is a very important theorem due to Abrams and Quinn. In fact, they're the ones who developed this notion of Frobenius algebra in C for this purpose, actually. What we get is the equivalence categories. Going from 2 TQFTs with values in C to commutative Frobenius algebra. And C. And the way it's done is to just send your TQFTs with value at the circle. Now, what's very cool about this theorem is we show the functor, basically. We show how to take a TQFT and spit out a commutative Frobenius algebra. But what this is saying is that if you see a commutative Frobenius algebra walking down the street, you can grab it and you can build a TQFT. All right. Any questions on this? Oh. Okay, we'll leave this one. Let's do an extended example. Yeah, let's do it up here. Let's do an extended example.
So some sort of commutativity comes for free. Some sort of commutativity
Yeah.
comes for free.
Commutative Frobenius algebra is automatically co-commutative. Yeah. Yeah. And it's not trivial to show. Kind of tricky to show.
Does it follow from the beginning right away? No.
Yeah, this shows like, yeah, I have a proof, but it's like, it's very, it's indirect.
Okay.
Yeah. Because you have to show like what you fix a co-product, you have a unique co-unit, and then some tricks. Okay, so let's do an example of how to take the unit of Frobenius algebra and use its corresponding TQFT. So let's take one of our favorite Frobenius algebras that's commutative. Namely, we're going to work over C. Let's just take this two-dimensional commutative Frobenius algebra. Polynomial ring and one variable mod x squared. I think I've been writing this. I've written this Frobenius algebra a few times. Okay, now what is a Frobenius structure? Here you have that delta. So this has basis 1 in x. So we need to describe, we know the multiplication in unit r, we need to describe the co-multiplication in co-unit r. So the delta sends 1 to 1 tensor x plus x tensor 1. The delta sends x to x tensor x. And the co-unit sends 1 to 0 and it sends x to 1. So that is the Frobenius structure. Now, a 2 will TQFT with values in T. This is going to be a functor that goes from 4 to 2 back. So let's draw some pictures. If I take just, I don't know, the ball, what I want to be able to do is break it up into these generators and relations. So I'm going to break it up as a cap and a cup, right? Now, that's going to get sent to a map going from C to C. First, I go from C to A via the unit, and then I hit this with the co-unit and land here. Okay. So what does this do? It takes my 1 and sends it to the 1, and then now this goes to 0. So this all, at least using this Frobenius algebra here, it's sent to the number, the scalar 0. Right? You're right with me? All right, let's do another one. Another shade. Let's do this shade here. So I need to take this and break it up into these generators. So I'm going to do hat. And then I have one input, and then I'm going to do some hands here. Co-hands, and then a cup. Okay, again, this goes to a map going from C to C. First, I do the unit. I land in A, and then I do my co-hands, which is delta. And then I do my hands, which is multiplication, and then I end this with co-unit. So what number does that give me? I get that 1 of C goes to 1 of A, goes to 1 tensor x plus x tensor 1. I multiply now, and I end up with 2x. And that now goes to the number 2. So I have that these manifolds go to different numbers, therefore these are different manifolds. So this TQFT helped me tell these apart, even though I can, you can eyeball it, you know how surfaces work. But at least it gives you numerical information on how to tell these manifolds apart. Now, this is not a perfect system. This is not a perfect system, because if I do this shape, perfectly fine surface, now I'm going to cap this off. This, I'm going to break it up like so. Okay. This is now going to go to a map going from C to C. I'm gonna get this with you, I go to A here. And then now what I do is I end up applying delta twice using co-associativity. And I end up at 3 copies of A. And then I apply multiplication twice and end up at 1 copy of A. And then I hit this with the co-unit. When you actually trace this through, you end up getting 0. You end up getting 0. So you don't get a complete invariant. In fact, you might want to choose a different Frobenius algebra, like CX minus cubed, to tell this picture apart from this picture. Okay. Also note that topologically, this surface is the same as this one here. And if you run this game, making it up with pans and copans and cups and caps and our favorite shapes. Okay, this ends up going to a linear map that sends your 1 to 0, as it should, because these two are the same, so it should be the same. All right, any questions on this?
Can you prove that you can distinguish all morphisms in board N to the different Frobenius algebras?
Oh, that's a question I haven't thought of. I haven't thought of, I mean, if you give me 2
Yeah.
manifolds, I could probably pick a Frobenius algebra that will do it through trial and error, but this is not my baby. This is, yeah, I do baby examples essentially.
Could you run everything here in positive characteristic? Was it allowed everything in positive characteristics?
Okay, we gotta be careful. We have to be really careful. Yeah, because I don't want stuff to vanish too quickly. That I don't know. Yeah, I would be a little careful about that. Any other questions? Okay, so I think this is pretty cool. It's really cool. So we have this really nice theorem. So this theorem is actually, it's like only the beginning of the story. You have this relationship between 2 TQFTs and commutative Frobenius algebras. And of course, you can tweak the left-hand side and get something nice on the right-hand side. So let's actually do some tweaking. Okay, so one way to tweak is, what we can do is just change the dimension. So if we change the dimension here, change that to like a 1 or 3, we actually need to change the structure here. We need to change the structural level. Okay, so here we're working with like algebraic structures in a little category. The lower the dimension is, the simpler the structure, the higher the dimension is, the more complicated the structure. Let me illustrate what I mean by this. If I wanted to look at, let's say, 1 TQFTs, okay, let's say in C. Well, you get the equivalent of categories, but essentially this is going to be like a certain alteration of the category defined dimensional vector spaces. And the reason why I kind of need to tweak this is because this category is not a group one. So you have to alter this category to make this big sense. Not all linear maps are linear isomorphisms, so we have to work with alteration of this. Okay, so we've gone from algebraic structures to like just vector spaces down a level. If we go up a level, it gets complicated. So three TQFTs. There's no straight answer for this. I'm not even gonna do equivalence. I'm just gonna do like a squiggly arrow. I'm being fuzzy here. But these have a nice relationship with these things called modular fusion categories. Overseas. So these are gonna be graded. And they're gonna be rigid. And they're gonna be rural. And they're gonna be like Boolean and linear and have a bunch of stuff. Boolean, linear, semi-simple. A bunch of flavor to handle this very complicated topological structure. Okay. So again, if we change the dimension over here, we have to change the structural line. Okay. Questions? Or my pictures have to go away. You take a picture. Okay. All right. Another way that we can tweak this is keep a level, but change the flavor of vortices. Change the flavor of vortices. So keep a level, but change the flavor of vortices. If we do that, we have to actually change. You can change the flavor of Frobenius algebra. Still keep Frobenius algebras, but we have to change the flavor. That's okay. They come in many flavors. They come in strawberry and orange. This one is grape. Okay. All right. So let me give you an example of this. This is theory due to Turner's riot in 2006. To riot in turn 2006. And what they do is they get an equivalence of categories. And instead of working with TQFTs, whose objects are oriented one manifolds, what they do instead is they work in the unoriented case. Unoriented case. Unoriented case. And the price that we have to pay to do that is on the right-hand side, we get these things called extended Frobenius algebras. Extended Frobenius algebras. I'll describe what they are. So, and it's the same thing, I mean, like, so Z here, going from the board category now without orientation to C. This gets into Frobenius algebra at the end of the day, but it's going to have some extra structure. So it's still going to come equipped with maps M, U, delta, epsilon that give you a Frobenius algebra. But now we have to take into account the fact that we lost orientation. So this category here, this board without orientation, this has two additional generating, tensor generating organisms. So you have the four corresponding to these maps, and we have two additional ones. All right, here's one. We lost orientation, so we need to be able to make up for that. So we have a organism that basically reverses orientation. I'm going to draw this. This reverses orientation. Okay. And then we have another map that is going to be going on the Mobius band. So I'm going to draw, I can't draw a Mobius band. I can't draw a Mobius band, but that's my estimate. This is going on the Mobius band. So that's what these generators are topologically, but they correspond to categoric phase. Well, this is a map going from A to A. And this is a map going from 1 to A. And here's how they're compatible with the maps in the above. First of all, we have that phi is a convenient algebra map. So it's multiplicative, co-multiplicative, co-unitable, and in natural these. And it's an evolution as well. So basically, this is the evolution of the Frobenius algebras here. And this map has some fun properties. Basically, I'll draw them in terms of string diagrams. So if I take theta, there's theta, and I multiply here and then apply phi, that's the same thing as just applying theta and multiplying. And here, if I take the unit and co-multiply and apply phi, you get this map here. Theta. Theta. Okay, so those are the conditions. All right. So, are there any questions on this? Okay. Now, I think these extended Frobenius algebras actually merit a study in their own right. So that's some work. I mean, these lecture series, I guess I'm supposed to like mention something that I've done. Here it is. I did some work on extended Frobenius algebras because I think they're interesting. So I'll tell you what we did. This is joint work with Augustina Chensky, who's a postdoc at University of Southern California. She's on job market this fall. Jacob Ketson, who was my former PhD student. He's now teaching at a fancy high school in Houston. And my former undergraduate research student, Avino Jimenez, who's now a grad student at UT Austin, University of Texas, Austin. Very proud of that. All right. Okay, so what we did was we studied of extended Frobenius algebras with Chensky, Hexton, and Jimenez. We didn't really care about the community part because this is really just get in there for Frobenius stuff. Okay, so basically, extended Frobenius algebras are Frobenius algebras with some extra structure. And we call this extra structure the extended structure. Okay. So the first result, just to get our hands dirty, was that what we did was we classified the extended structure for well-known examples of Frobenius algebras. So the extended structure of the Frobenius algebras below are classified. So we did this for C over C. We did this for C as a Frobenius algebra for R. We did this for several cyclic groups. And 1 and 2, 3, and 4. We did this for the 4 and 4 group. And we did this also for our favorite types of examples, polynomial ring and one variable modified by x to the n. So most of these are trivial, but we get some interesting answers for these cases. I will say we did this before AI. Okay, so we did this all by hand, which don't recommend. But I would say open, do more, and use AI, use it to help you. Maybe you can get general patterns of what these structures actually look like. Maybe you can knock out all the signatures or even delve into matrix algebras, etc. So the first thing we did is actually classify these maps, and Willie's got to start.
Sorry, what does this notation mean? C over C, C over R?
C as a C algebra,
C.
C as a R algebra. So that you have an underlying vector space, the real vector space.
Viewing characteristic P, group algebras of cyclic groups are the same as truncated polynomial rings. So the two families would coincide in characteristic.
Yeah. You like characteristic P. You can tell I don't. Yeah. Papa wanted me to rewrite that one book and open characteristic, and I was like my eyes started twitching. This is being recorded.
Classification means according to the dimension, right? The algebra.
No, according to, we basically take some Frobenius algebra and we classify these maps that make them extended. Yeah.
Does the term extended make sense for non-commutative Frobenius algebras?
Yeah. So the only difference here is that you require
Mhm.
A be commutative or not, so we can pick off the ones that are commutative. Actually, they're all commutative in this case.
Those are the ones that enter in the theorem.
Yes, yeah, you need commutative proof here.
Yeah, but in general, it makes sense. And,
Yeah,
mhm.
we can do it. Another thing that we did, so, which, I have time, okay. So here's a fact that I mentioned 3 times, and now I'm actually gonna write it on the board. Finite dimensional Hopf algebras are Frobenius. Finite dimensional Hopf algebras over C are Frobenius, and there actually exists a Noodle version. There actually exists a Noodle version, but you have to use integrals. You have to use a little bit of integral theory. If you know Hopf algebra theory, that's one of the most important things you need to learn. It's a certain type of element that helps rule the Hopf algebra. So what we did is that we introduced the notion of an extended Hopf algebra in C. And we showed that it's extended Frobenius. And we also did this factorial thing, this nice function that gives us this. I thought that was nice. So we're kind of like increasing in complexity. There was stuff more in field, there was stuff on the Hopf level. Then our last result, we really kicked this up a notch. So now we're going to be interested in extended Frobenius algebras as a whole, really. So we introduce the notion of an extended Frobenius monoidal functor. Extended Frobenius monoidal functor. And in order to check that this indeed is the right definition, we showed that they do indeed form a category. So the composition of these have to be one of them as well. That was actually the hardest part of this. We showed that they form a category. And then we also showed that they extended Frobenius algebras to extend Frobenius algebras as they should. They should. And I'm particularly proud of my former undergrad who worked on this because like when I pick problems for students, I try to have a level, like different levels of complexity to see what they like. And I have something concrete, and I have something intermediate, and I have something super abstract where I didn't know the definition at all. And I thought, well, maybe he will want to get his hands dirty on this, but he went straight for this, which I was really happy about, straight for this. Yeah. So yeah, those are our. And then, I mean, open, we could do extended Frobenius monads and connect them up. I mean, there are lots of different directions that you can go, which may come to light after the next lecture. Are there any questions on this?
If you have time, can you say a word about what extended algebras are, like over the complex numbers?
Maybe afterwards, because then I have to talk about.
Of course,
Yeah.
yeah.
Ooh. Okay, I think I'm gonna take 5 to 10 more minutes. But if you have to go, please feel free. What I want to do is basically make sure that we don't mix this up with what's called an extended TQFT. So I really want to make sure that I give that some justice, so. And now to the last bit. There's a whole industry and studying these TQFTs, and I just want to show you some of the flavors. This is another one. So not to be confused. Not to be confused with these things called extended TQFTs. And this is the last bit. So basically what these are symmetric familial functors, but I'm going to say higher functors. In particular, I'm going to say n minus d functors, so these numbers are going to make sense in a bit. Between certain n minus d categories. So now I'm going to work with higher categories, where n is strictly less than 15. Now, on the left-hand side, what I do is take a look at topological. This is going to be a board category, where I start with n minus 1 all the way down to d. And here, objects are going to be d manifolds. Maps, one maps, I should say, are going to be d plus 1 manifolds between the n manifolds, and so on. So n minus k maps are k maps or k manifolds, where here I'm starting the k at d. Okay, and then you want to preserve organization. Okay, so that's all the stuff you want to keep track of on the left-hand side. Now on the right-hand side, we're just going to take an arbitrary d n minus d category. These form a category. Which I'll call n minus 1 down to d TQFT. Well, values in d. Now, there's a nice theorem in the case where we have 2, 1, 0. 2, 1, 0. So here we're going to use two categories. This is due to Chris Schaumer-Kreis. I think it's a lovely theorem. In fact, I did this in his thesis. So for this, we need to consider the two categories, which I call bins. This is a two category. Objects are going to be just C algebras. Those are the objects. Your maps, the way you link to C algebras, are going to be phi modules. Phi modules over C algebras. And the way that you link two phi modules, in other words, your two maps, are going to be phi module maps. Okay, so those are your objects, your maps, and your maps between maps. All right, these form a symmetric removal two category. Now the theorem, this is due to Schaumer Priest. In 2009, what he says is that there exists a two equivalence, an equivalence between two categories of 2, 1, 0 TQFTs with values in this category BIM with, remember, we still have this level 2, so we're gonna have some sort of Frobenius algebra, just have to change the flavor of it. Frobenius algebras over C, except they're gonna be symmetric, and they're also gonna be required to be separable, and we're gonna consider this up to or equivalence. So I think this is really beautiful, actually. And if we have such a two-functor, we get all this stuff by taking its evaluation at the time. The symmetry basically takes care of orientation conditions here, and the separability takes care of the extension down to a point conditions over here. All right, the story goes on, this TQFT business, but I'll stop here. Thank you very much for listening.
Questions?
I don't know if this question makes any sense, maybe it's, but I'll ask it anyway. So if you somehow define this board as a category of a Frobenius manifold, which is related somehow to Frobenius algebras.
It's like WWW,
Yeah, too many Frobenius.
Yes, too many Frobenius, yeah.
I mean, do these TQFTs tell us something about the Frobenius manifold, maybe?
I don't know, I'm sorry, yeah.
No, it's-
But I mean, like, the names are kind of begging for that question, but I.
Yeah, exactly, the names are making that question.
So you started with general non-commutative Frobenius algebras, and now in TQFT we encountered only commutative Frobenius. What can we do to get more than just commutative?
So there are TQFTs that don't need commutative
Mhm,
algebras.
mhm,
So possibly I would say whatever those theories are
mhm.
that incorporate orientation, if you're going to draw orientation, or if you're going to use these algebras.
Yes, yes.
One kind of point.
Mhm.
And yeah, I mean, you can run this game with AI and you can plug in the commutativity condition to AI, you get a bunch of commutative examples. So that's why I don't think commutativity is that big of a deal, because you can remove it and still have applications, or you can impose it and have interesting computation.
How many different
Structures.
yeah, you get in this particular question? What is the complexity? Right.
Yeah, so it's kind of funny, like most of the cases are trivial.
Mhm,
So by trivial, I mean like this is the identity map, and this is like this zero.
mhm,
So trivial,
mhm,
trivial for N is 2, not trivial for N is 3 and 4. It's starting to get interesting,
mhm,
like what's the unity plan? Oh,
mhm,
interesting
mhm.
minus signs here, and this is trivial only when N is odd. When N is even, you get something interesting. Yeah.
Does it have to do something with Frobenius algebras and super vector spaces?
I don't know the intuitive reason for that. Yeah.
Mhm.
Yeah. No idea. The N is odd. It's just trivial, even.
But this object does exist. The Frobenius algebra in a super vector space does exist. It's a question.
Yeah, and then also you can always make an extended structure in a very trivial way. By trivial, I mean this is the identity.
Mhm.
Yeah.
Additional questions? Let's thank Chelsea for this very